Hello everyone, welcome to the webinar this week. So coming with us today is Professor Shawn Wang from the University of British Columbia. He is an expert in the field of convex analysis, optimization, and its applications to signal processing, statistics, and communications. So today he's going to tell us about the rules of identity operators and proximal mappings, classical platform circles, and vectors. So please, the stage is yours.
Okay, thank you. Thank you, Hao, for the introduction. And thank you, thank the organizer for giving me the opportunity to speak today. Okay, so I will talk about root of identity and proximal map. Try to see the connections, how the cycle gap vector related to those concept. Yeah. So let me do next page. Yeah. So here's the abstract. I'm going to use Attouch-Théra duality to study cycle and gap vectors of composition of proximal mapping. Okay. So when the cycle and gap vector do not exist, I will come up with concept called phantom cycles, phantom gap vectors. Okay, that's our approach in year 2020. Then when Stephen Simon read the paper, he approached it in a different way. He provided a lemma for support function closed to convex set, then study the problem from a different perspective. So after that, we extend his lemma to closed convex functions, and how, because his approach is quite different, and we show the connection of his stuff to Attouch-Théra duality, and see how it connects to phantom cycles, phantom gap vectors. Okay, one of the the consequence of Stephen Simon's result is we can study the cycle gap vectors for any isometry map instead of the shift operators. Okay. So now let me here's the outline, but I will talk some of them not covered. Yeah. So let's start with the first one. What is a cycle of a composition of proximal map? So the setup is a Hilbert space. Everything is a Hilbert space. And the set of lower semi-continuous function is denoted by gamma 0 x. So in the product space xm, so delta denotes the diagonal set. Okay, x belongs to x. Delta is a diagonal set in bold x, So the right shift operator from x to x, you can see here, I do the right shift, you can xm, then it's defined that way. Okay, the product norm is given this way, and the separable sum for functions is denoted in this way. Yeah, separable sum. So the proximal map, and for convex analysis, will everybody know, is denoted by this, the identity plus subdifferential convex function, the inverse map. Right? It's a firmly non-expansive. So given that the function fi, right? Finite number of convex functions. How do we define a cycle for that f? It's a vector defined in this way in the product space, such that you can see I do z1 prox f2, then give me f2, right? Then z2 prox f3, give me z3. Then keep on doing, I have zm minus 1 equal to prox of the earlier vector using proxmap of f minus 1, I got zm minus 1, right? Then eventually I reach here zm prox fm, zm reach to fm, zm, right? But here zm after proxmap f1 goes to z1. Okay, it's a circle, right? So it's a cycle. So we try to quantify the cycle of the finite number proximal mapping, right? Finite number, that means prox f1, prox f2, prox f3, and prox fm. Those z vector form a cycle. So in the framework of operator in product space, it can be written in this way, right? Prox f, rz, with r as the redshift operator. In terms of monotone operator, you can write in this format. Okay, so z minus rz is the difference here, right? Plus partial here equals 0. And this corresponding to the fixed point of the prox map F composition with R, right? Those two composition and give you a new map, but this cycle is exactly the fixed point of that map. So the notation we shall use is a functional conjugate. We know it's defined as usual. The infimum convolution for two functions is defined in this way, right? So it's exact at x if there exists y, such as this is true. Okay, subdifferential as usual, given by that subdifferential convex function. So also indicator function as defined before, the prox map of the indicator function is a projection on the side C, right? So then we also involve some mapping, say n going from xx is non-expansive in this way, right? Firmly non-expansive. If 2 times minus identity is non-expansive. Also some other mapping called beta coercive, mean beta time n is firmly non-expansive, right? So for some constant beta from here, I do this, it's a firmly non-expansive. Then I call n is beta co-coercive. So the fixed point set is defined this as usual, okay? Monotone operator A, then we define A tilde in this way. Then that's again, another one is called another monotone operator. So the blanket assumption for the function is given all the fi, finite number of proper lower semi-continuous convex function, and the conjugate of f star, right, plus this, and I will require here not empty. Okay, that's the blanket assumption. And it requires this is equivalent to f infimal convolution with the indicator function of delta is a proper convex function possess a continuous manner. Okay, that's the assumption on function and the conjugate. Okay, this is the assumption. So one of the key tools we study is this cycle and gap vectors. We need is Attouch-Théra duality. Okay, so suppose I have A, B, two maximum monotone operator. If I write the primal solution, 0 belong to AX plus BX denoted by S, right? Then you have the dual program is called found X star such that 0 belong to A inverse. So B tilde, remember my B tilde is defined as some other fancy object like this, right? A tilde. That's so I use B tilde to in the dual. Okay. So S is the primal solution set. S star is the dual solution set. So you can recover the primal by using the dual solution in this way. You can recover the dual solution by using the primal set in that way, right? So they can recover each other perfectly, okay? So now for the shift operator we introduce, and Hans and I, we have obtained some property about this identity minus R. This R is the shift operator, always non-expansive. Therefore, identity minus R is a maximum monotone. And the inverse map of that is 1/2 identity times this, okay? T is given by this, the skew operator. That is a normal cone operator. Therefore, this guy actually is give you strongly monotone operator. Some other property about a skew operator, okay, is given in item 3. So for some basic property about the subdifferential of convex functions, right? Basic property is say if this is not empty, f has to be lower semi-continuous, and you also in general have this subdifferential relationship, and some basic property about the infinite convolution of two convex functions. If they are exact, right, there exists a y such that this infinite attained infinite convolution is exact at y, then you have this subdifferential relationship. Okay, if this is not empty, intersection not empty for x and y, then the infinite convolution at x is exact achieved at y. Okay, the subdifferential is given by that format. So when you study the cycle of finite number proximal mapping, the set, so if the argmin of the individual function not empty, intersection, okay, intersection not empty, then the cycle Z actually is simple. The cycle, the set of cycles, essentially all the vector to be the same. Z with Z belong to S. S is the intersection of the minimizer. So therefore, it only make sense when we're talking about the case which is this guy here intersection has to be empty. If it's empty, then we talk about the cycle vectors. Now let's see what the classical cycle and guide vectors. We want to put that in the framework of Attouch-Théra duality. So now, so we have the cycle quantified by something like this: 0 belong to partial f x plus identity minus r here x. Okay, then you use Attouch-Théra duality. You can put this into the primordial format like this. Okay, so then the surprising thing is this: if you look at the dual, this guy have a very nice property. It's a strongly monotone operator. Therefore, what you get is found that the solution of the dual problem is at most singleton. Okay, it's at most singleton, possibly empty. It may not have a solution, but it at most one solution if it has. The key problem is, as we said before, because this guy is a monotone operator plus this is strongly monotone, and give you that. Okay, so now the classical cycle and the classical guide vectors. So if you write it into the set format, give you that, right? Therefore, you can go from, you can recover the cycle from the gap vector, okay? And you can also recover the gap vector from the cycle in this way. As we said before, this gap vector set, the set of gap vector is actually at most singleton, okay? Also, this y belong to the diagonal perp, the perpendicular subspace of diagonal. Now, what happens if, say here, if this Z is empty? Yeah, is so because by Attouch-Théra duality, it says actually Z is equal to empty if only if actually equal to G equal to empty. Those two sets actually have a nice relationship. Okay, so what happens if Z is empty? If Z is empty, we come up with some fancy vectors so that you can recover the classical one when the classic one do exist. Okay, so now in order to do that, we have to play with this primal problem and the dual problem, try to do some kind of like enlargement, monotone enlargement. So extending the dual. So the dual problem is this, dual problem is that, then use the fact on this operator, what I got this, right? Then you will put this and that together, you have that. Then I have enlargement because the subdifferential of a convex function, subdifferential another convex function is always subset of the summation. So that's larger subdifferential. Then keep it here. Yeah, then the surprising here is what? The surprising here, the T is a skew operator. This is a maximum monotone operator. Therefore, together they're maximum monotone operator. Okay, then here is identity. Okay, now the dual, the enlarged dual become like this. Now the key, the nice result for this is you found this is the maximum monotone operator. This is the maximum monotone operator that then you can apply Minty theorem in convex analysis. Minty theorem says have a solution. Before the D, the D problem is given by Z, okay? But it may not have a solution. But after you do the enlargement, it does have a solution in here by Minty theorem. This you can call it phantom gap vector. This is this coming from imagination. So for the gap vector, okay. So we say this is the gap vector for the proper lower semiconductor function given by this, okay, F infinite convolution delta. Okay. Now you can do this problem also from the perspective, from the view of primal problem. Say the primal problem you have this, right? But this, the problem with this one is, this is the maximum monotone, full domain. This is the maximum monotone. And the addition together, they must be maximum monotone by Rockefeller, one of the results by Rockefeller, okay? Then you cannot do the enlargement here. Therefore, one has to reformulate this one. Instead of enlargement, we do the reformulation. So you see, this is you rewrite that one as this, right? But this belong to delta perp. Therefore, this belong to this intersection. It's kind of like a parallel sum for two monotone operator later. So then this is a monotone operator, this, right? Then, but this is a subset of infinite convolution of two functions, okay, subdifferential. And therefore, we can, well, this stuff, subset here coming from the infinite convolution of two function property, subdifferential. Therefore, we have this subset of Z, right? It belongs to here. Then if you look at this, then now you have a monotone inclusion problem like that. Okay. Now this is surprising after you do this. Okay, this guy always have a solution. Before the problem here, we have this. Okay, this guy may not have a solution, but after you do those manipulation, do some enlargement like that, this guy always have a solution. Well, this is called a phantom cycle of this function, Okay, phantom cycle. Now we can rewrite in the primordial format Attouch-Théra duality. Okay, consider the Attouch-Théra primordial problem, and the primal is this, right? Primal is that, and the dual is this. Okay, then the turn out that d tilde is the Attouch-Théra dual of this p tilde, and d tilde has a unique solution, right? Because d tilde has non-empty solution, my p tilde should also have non-empty solution. Okay, because this restriction, and it gives you unique solution. But if you don't have this restriction, and this will usually have infinite many solution, it's called the cycles. Okay, so now, so the process, what you can prove, yeah, you can show that indeed the Attouch-Théra dual of the d tilde indeed give you p tilde. Okay, indeed give the process is given here, so I will omit the process. Okay, so the process essentially give you how do I got say that I compute the dual from here go to here. Okay, it gave me the exact the right Attouch-Théra dual. Now, how does this related to the the classical cycle, phantom cycle? How do they relate it? So the following theorem, the theorem number 1 says here, suppose let X be a phantom cycle of this guy, okay? Then that means that is my X has to be a solution of this. Now, if the following is true, if the infimum convolution, okay, for that is lower semi-continuous at this X, okay, lower semi-continuous, and this guy is exact. If that two condition is verified, then my X will be written, can be decomposed as two component, U plus V. This V belongs to diagonal, and my U is exactly this U here become the classical cycle. Okay, so under this two condition here, this condition 1, condition 2, then you can get, then you can recover the classical cycle. In other words, the classical cycle, it will exist and you can recover it. Now, classical cycle can become a phantom cycle if you do a shift. So let this one in the product space, okay, this is in XM, right? Let U be a classical cycle, that is this, okay? Now I set V equal to this stuff, that belong to diagonal, and X equal U plus V. Then some mathematical work give you that this infimum convolution will be lower semi-continuous and exact at X. And this X equal U plus V will be a quantum phantom cycle. Verify this verify 26. Therefore, X is a phantom cycle. So the difference between that, the classical one U and the phantom cycle is just a plus a vector. This U, this V has to be in the diagonal. Yeah. So now the following result essentially summarize the relationship between the classical cycle, phantom cycle, and gap vectors. Now, recall that in theorem, we always have X, Y exist. X is a phantom cycle, Y is a phantom gap vector. Okay, so then they have this relationship, or that's because Attouch-Théra dual. But how do they relate to the classical cycle? So the classical cycle vector always is a set equal to x plus delta. Okay, this x plus the delta set, an intersection, right? Because this intersection of two sets here may be empty. Well, x always exists, z may be empty. Okay, so the cycle z can also is a subset of this, some other. This is just a fixed point set of the cyclic proximal map compositions. Okay. Now you can quantify the classical cycle in the following way. Was not empty. If only if, you see, it relates to the lower semi-continuity of this F infinite convolution with iota delta. Yeah, this function has to be lower semi-continuous and it's exact. Okay, so those they are equivalent. So the function the composition, the infinite convolution function here is closely related to the cycle vector. Another way you can say this is equivalent to the parallel sum. So this is a parallel sum of two subdifferential. Parallel sum of the subdifferential is not empty at x. Okay. So if that happens, then classical cycle, the set of classical cycle won't be will not empty. Okay, so typical example you get, a simple example you can get in this way. You look at the C1, C2, the say set C1. I have a say e to the power x minus x stuff, right? Then C2, C1, C2 here, C1 here. But if you do the projection, okay, you do the projection, you have this, then here, then you do that, then do this. Essentially, you don't have a gap vector. Okay, you don't have a gap vector. But then, you don't have a cycle, you don't have a gap vector. But then, if I look at iota C infinite convolution, with a diagonal set, this always have a generalized cycle and always have a generalized gap vector, which given by this. Okay. And some other example, we quantify the line. Yeah, I find a number of lines in Hilbert space or in finite dimensional space. Is a classical cycle, not empty, always not empty. It has a unique cycle. If only if how does the direction here, VI should not be parallel. Those, okay. So the question is, of course, then you say, how do you find this phantom cycle and gap vectors? How do you find it? So let's come back to Attouch-Théra dual primal dual. Then you have this relationship here, right? Now you denote this by the G, okay? Denote this, or this function is important for the study. So denote that one by G. Then to find the cycle vector or gap vector, you can apply forward-backward method, okay? So this is, of course, this is relaxed with some parameter move around, say xn plus lambda here times this, right? If lambda equal to 1, always equal to 1, then I will get say the proximal, it's forward-backward method, okay? So, but this is relaxed with parameter lambda n here. So for that forward backward method here, your xn always weakly converted to x to a general cycle. And this, the difference Rxn minus xn, always converted strongly to the generalized or phantom gap vector. Okay, so the method to find that is forward backward method to find those vectors. Now, now I want to go approach the Stephen Simon's point of view. How do we connect his work to ours? This is where you can, if you like to ask me questions, I can answer. If not, I will move to more general format. Rather than the shift operator, I now deal with isometry. Okay, now I deal. Now, Simons gave a different approach. Simons essentially is more abstract point of view. He considered the root of identity of so he has a linear operator r to the power m is equal to identity. Okay, now he defines this. He defines the average is given by that. Okay, now for him the important object is y equal to the kernel or the null space of that linear operator a. Okay, now he defines S to be this, R minus identity, and Q to be this, right? Then he gave a nice relationship about those linear operators. Okay, so the range of S and Q, the property, and those essentially just summarize the relationship between those two different linear operators. One of the key objects he observed is this: if R is isometry, if R is an isometry, then you always have this nice relationship. Okay, so let's call, you see my S equals this, S equal to that R minus identity. Okay, what's my R? R is the mth root of identity operator. Okay, now if you look at that mth root of identity and some classical examples, okay, so even you have Rm equal to identity, that does not imply R has to be a non-expansive map. Okay, does not imply that the matrix is non-expansive. So Bombay Choa matrix, this guy, okay, b to the power 5 equal to identity, but it's not non-expansive. Okay, so similarly, you can deal with identity, but it's not non-expansive. And Turnbull matrix, and you have this b to the power 3 equal to identity, but it's not non-expansive. Those examples are inspired from the work from Nicholas Hegem, the matrix book. Okay. So, however, you have the following result. So if Rm equal to identity, R is linear, okay, then the following is equivalent. R is non-expansive, isometry, they are equivalent. Okay, so that is the property. We will use that one later often. Yeah, so as we say before, so the operator A, and the null space y, y equals null space of A, yeah, is important in Stephen Simon's work. And we realize that, we show that his averaged operator A here, where is it? This A here, actually, yeah, this operator A actually is just a projection. this operator will show that the kernel, the null space is essentially a fixed point set of R, the orthogonal complement. And the A actually is a projection on fixed point of R. Okay, so range S equal to this. Okay, so and he used this null space Y for his analysis. Now, now we essentially the condition here, the condition, if you do not assume R is isometry, this theorem is not right. Okay, that's why we gave you the example earlier. Use B2, you found that the result is not right. Now, Stephen Simon shows the following result for f equal to the indicator function. Okay, indicator function. And he shows this. Suppose f is a proper lower semi-continuous function, and the y space intersection dom f star not empty. Okay, again, it's a condition on the functional conjugate. Then there exists a unique pair of vectors, ED, okay, associated with F, right, belong to Y a product space such that D equal to SE equal to QD, such that the conjugate of F star verifies this inequality for Y belong to the null space Y. Okay, he shows that. Okay, then he used that to quantify the cycle of for projections. But we are trying to do here is we are doing it for proximal mapping instead of projection. Now, a further property of that is this is everything in Y, right? But we do that, you can put that one in term of, in the space X. Okay, you have this result. Now, now we show that his vector here, his vector E and F, is a magic vector E and D. Okay, his stuff here actually is just a Attouch-Théra duality solution. Okay, let R be an isometry. My Y equal to fixed point set orthogonal complement. F is a proper lower semi-continuous convex with that requirement. If DE is given by the lemma, okay, then you consider the Attouch-Théra problem, primordial. Then E and D is a solution, to the primordial solution here, problem here. If you do more restriction on the primal here, okay, you do the X belong to the null space, then ED will be the unique solution of the primordial solution. Or ED will be the unique solution. Okay, if you don't do that restriction, you may get here many cycle vectors, phantom cycle vectors. Okay. Now we can use this ED to this ED vectors, try to connect to our result before for the phantom cycles, phantom vectors. Okay, so you can use that ED, try to classify, to quantify the cycles. Okay, so let F be a proper lower semi-continuous convex function, and with this requirement on the dual, okay, if ED is given by the lemma, yeah, then you have the following. That is a cycle, classical cycle, if only if this relationship, the F star, the functional conjugate, evaluate F as Z plus Fz equals this equals 0. That if only if Sz equal to D, right? And again, this kind of stuff show up. So the F infimum convolution with this is important for the work. Okay, SD equals that, my FZ equals this, or another way, this has to be equals this. Okay. Now the proof essentially try to use the earlier result lemma, which is given by, which is you see, let's say 1 to 2. Okay, we just went too quick. 1 to 2. If I have that, I write out the differential inclusion format, then use the definition of S, then you have this. That's Fenchou-Yang inequality. Okay. Now 2 to 3. 2 to 3 is more involved. I have, if you assume this, okay, then I have this. Then by the lemma, now I use vector E and vector E property. I have this. Then if you add in that, you have this. Okay. Now use one of the key property in Simon's lemma. You have this. Okay. Then you plug that one in. You got SZ equal to SE. Okay. Then some simplification give you this result. Okay. Now 3 to 2. 3 to 2. You have to use so 3 to 2. If you with this, you have to use this assumption and use this also. Then you have essentially you can get the item 2. Okay, so the proof is all here, but they use earlier lemma to try to move forward. Now this is the result is try to quantify the cycle, right? Then you have 1 to the 4 equivalent relation here. So now we try to say under what condition this one hold, under what condition this one hold. Okay, so we single out 2 class of functions. So the first class of function is translation invariant functions. So we say F is translation invariant with respect to set C be subset of X if this one is true. Now, if F is a proper lower semi-continuous convex, C is closed linear subspace, and F is translation invariant with respect to C, then you have this result. You have that result. Okay, the Fenchou conjugate this equals this, but give you the closure equals this. Okay, then of course then you can apply the main theorem. You get a quantification of the cycles. Okay, then Z belong to here. That is a classical cycle. If only this and that, because I have translation invariant stuff, that condition here automatically hold. So I only need to check SZ equals D. Okay. Now the next class of function is we quantify the minimizer of F. Okay. So with this assumption, as usual, let ED be given by the lemma, right? That extended Simon lemma. Then suppose my Z is belong to argmin F at Z equal D. Then you always have this. You have closure of this divided E will be equals to this and equal to FZ. Okay, so that is another quantification for the minimizer. Therefore, this gives you the quantification for the cycle for when the Z belong to millimeter, Z, suppose Z belong to a millimeter of F, right? Then Z is a cycle if only if this is true, if only if SZ equal D. So the key example for that is we are dealing with F for the indicator function, this. In this case, you recover the sequential projection cycle. Okay, so I have essentially, so here that is a cycle for projection maps. If only this, if only that's true. Okay. Now the final concept I want to show you that is, again, I want to show you that phantom cycle gap vectors for arbitrary isometry map. Okay, so before my is a redshift operator. Now because Stephen Simon's work, we can deal with for arbitrary isometry map R. Okay, talk about cycles and gap vectors. Now, because that lemma, we have the following result. The phantom cycle, phantom gap vector always exists. So you have to apply the lemma to what function? We apply the lemma to the function to the closure of this guy. Okay, so let F belong to a proper lower semiconductor convex function with this assumption. Okay, verified. Let ED be given by lemma, the extended Simon lemma. Then the set of phantom cycles of F, okay, is given by this set. This E plus Y perp. Okay, Y perp is fixed R. Okay, so the phantom gap vector of F is the gap vector of gap vector this, but associated with this. Okay, this D equal to SZ for any Z from here. Z is from belong to the capital Z. Okay, this phantom cycles and phantom gap vector always exist. Again, okay, this for Z. So our R now can be any isometry map. Okay, so let me summarize what I tried to say. Yeah. So the key approach to study this work is Attouch-Théra duality. Okay, primordial relationship. Then to define the phantom cycle and gap vectors, we have to use this kind of stuff. Okay, so infimum convolution with iota delta, the indicator function. Then to find the gap vector or the cycles, we can use forward-backward algorithm. Then the question is, how do you deal with maximum monotone operator? Well, that's kind of tricky because I don't know how to do the monotone operator analog for that. Yeah, that is work Hans and I are working on, and we make some progress, but there's still some difficulty to settle. And the paper I'm talking about is item 2 here, and the future work we got in the proceeding. It's all in the archive you can download. Yeah. Then the Simon's paper is also in the proceeding. It will appear. I'd like to thank you for your time, for your attention. Thank you.
Thank you very much for your beautiful talk. So now is the time for questions and comments. So everyone just unmute yourself and then ask question.
Shawn, Would
Yeah.
you just mind putting the references back up again? Just
Thank you. Let me.
thank you.
Yeah, thank you.
Thank you.
Yeah, thank you.
Just wanted to write them down.
Is they are available in archive? I can send it to you also.
I can get it off archive. Is the Simon's paper also an archive?
Yeah,
Thanks.
yeah, thank you.
So if is any questions and then comments for the talk? So if we don't have any comments or questions, then it joins me to thank our speaker for the very interesting talk on the psychovectors. So thank you, everyone.
Thank you. Thank you all. See you in Canada.
Hopefully.
This weekend?
No,
Thank you.
no, next week.
Next week.